So today we're going to start looking at complex numbers. So this is going to add a whole nother layer to the numbers that you're accustomed to using. And complex numbers kind of have a long history, so we'll be reading about the invention of complex numbers and which happened during the Italian Renaissance in the 1500s. And we'll see some of the players involved in that. I think it's a pretty dramatic story, so we'll read about that next week. There's some interesting Italian names involved, like Raphael Bombelli, Emilio Cardano, and there's some pretty exciting mathematics, how it actually developed. So quadratic equations, like we've been solving, parabolas, right? Human beings have known about parabolas in different civilizations, especially ancient Greece, but the Chinese and Indians also were aware of them. They didn't look at them using the same notation and stuff that we do today. They worked with problems that were parabolic for over 2,000 years. There were some problems that were parabolic, though, that they just thought had no answer, or they couldn't figure out an answer to them. So it caused a big problem in mathematics for about 1,500, 2,000 years. Then these Renaissance guys came up with a way to fix that problem by kind of inventing, whether math is invented or discovered is a philosophical issue. So we'll say that they discovered this complex nature of numbers. So all the numbers that you guys are used to should fit into this box. So we've got like integers, right? Are integers really specific or really general compared to all the other kinds of numbers that you know? Specific, because there's more general types. So I'm going to put the integers right in the middle of this box. I remember in middle school I went over this a whole bunch of times. I used to get really tired of it, but today we're going to take it further. So integers like 2, 3, those are elements in the set of all integers. I'm imagining this is the set of all integers. Obviously there's an infinite number of them in there. Okay? 2, 3, negative 3. The next most general kind of number is something that you can make into a fraction. All integers are fractions, so they're inside the fraction bubble. But there's other things that are fractions that aren't integers, like what? Give me an example of a fraction that's not an integer. 1/4. 2/3. Negative 3/5. Those are all fractions, or rational numbers, but they aren't integers, so I'm going to do those in red. So that's a lot bigger size of infinity. So things like 2/3 and negative 5/7. Those are fractions, but they aren't integers. That's the rational numbers. There's a lot more of those than there are integers, because they fit in between, Then you guys are aware of another type of number that's even more general than the rationals. And those are the irrationals. What's an example of something you can't make a fraction, something that is irrational? You guys know several. What? Pi. Nice. And some of the things we're working with in this chapter, we've seen a bunch of them already, like the square root of 67 from a second ago. That's irrational. It continues forever, but it's got no pattern. Things that continue forever but have a pattern are things like 2/3, 0.666666666. If it has a pattern, it's rational. You can make it into a fraction if you're clever enough. But if it doesn't have a pattern and goes forever, it's irrational. So we've seen lots of those numbers already as well in our mathematical career. Am I drawing any particular shape here, guys? What do you think? Nah. So we've got things like pi out here, things like the square root of 2, things like negative square root of 67. There's a whole bunch of those. I've got a great video we'll watch that Ted produced on how many irrationals there are versus irrationals. It's higher level math, like way beyond calculus. It's built for high school students. We'll watch that one of these days, maybe tomorrow. A little short clip. Anyway, so there's some empty room in my box, because from what you guys knew, this green bubble right here that includes the integers, the rational numbers, and the irrational numbers, we had a name for that. You've been using it a lot this year. Those are the real numbers. See, but I'm talking about the complex numbers today and their discovery during the Renaissance. There's some other room in my box. What else is left in that box that's not an integer, not real? Imaginary numbers. That should make sense. That's why they called them imaginary numbers. Now, when I first learned about them in high school, I thought, well, they're imaginary, so like, who cares? If they're imaginary, like, why are mathematicians just wasting their time discovering them and using them for things? Like, who cares if those two equations right there don't have any real numbers? Then, like, forget about them. And people did for over 1,500 years. But remember what time period they were in. This is like the Middle Ages and before the Middle Ages. That's what came right before the Renaissance. Was there any good technology back then? Well, yes, but like, there was no electronics. One of the reasons there were no electronics is because imaginary numbers are the key to electricity. That's, even though they're imaginary, that's just so we can think about them a certain way. They are the way that electricity works. They're the way that a lot of modern technology works. So they're not irrelevant even though they're imaginary. Does that make sense to you guys? And you can't see a lot of that, but there's a couple applications in our book that'll show you how they do stuff with electricity even at this level. So you guys will get to see a little bit of that. So where do they come from? Well, they come from this guy named Bombelli, we're going to read about him, thinking about what the most basic problem was in parabola land. And the most basic problem in lots of parabolas when he was journeying through parabola land was he needed to calculate the square root of -1. So how do you calculate the square root of -1? Well, I mean, how do you calculate the square root of 25? You guys know it's 5, right? But think about how you know that. You know that because, like, 5 times 5 is 25, right? And you could also think of it as like, okay, well, like, if I put a plus or minus out here, I can abstractly think about, like, well, -5 times -5 is also 25, and that's kind of where the plus or minus thing comes from in the beginning, right? Well, try to do that with -1. Well, 1 times 1 is 1, not -1, so -1 times -1 is 1. You can't mix and match because squared means squared. It means do the same thing, right? So is some fraction going to work? Like 1/2 times 1/2? No, that's a fourth. How about like 1/4 times 3/4? Well, no, that's like 3/16. And you can play this game forever until the end of time. Well, people did for like 1,500 years, so they're trying to figure this out. And they were not successful. So eventually in the Renaissance, this guy named Bombelli decided, you know what, I'm just going to call that something. I'm just going to accept that this is something unique. And so he decided to call the square root of -1 I. Instead of just ignoring it, he said, I'm just going to call it something, and I'm just going to start working with it and see what happens. And keep working with it and keep working with it, and that's what human beings did. And they eventually made some other big discoveries by just accepting that we're going to call this I. And that's why they called it imaginary. I'm sure in Italian it was not called imaginary. I have to look up the Italian word. You guys get the point, right? So, complex numbers, these are all complex numbers that you're used to, except you haven't been thinking of them that way. There are things that are strictly imaginary, like I floating around out here, or 2I, which is the square root of -4, or 3I, which is the square root of -9, or -7I, which is negative square root of -49. Does that make sense? But then there are also things that are kind of some of both. Things like 2 plus 3I. We're going to see those right away today. Those are complex numbers because they have a real part and they have an imaginary part. So those kind of also fit into our universe of numbers. Those would be kind of the intersection. Let me draw this more precisely. If this is all the imaginary numbers, then there's a big intersection here. I should really draw this bigger. But things in here are like 2 plus 3I and stuff like that. You don't need to visualize this super well, but that's the idea, is that we've just broadened or generalized the numbers that we're aware of. There's even more broad general numbers than this. Like my wife did a project in college. They're called the quaternions in the late 1900s, where they had 4 different kinds of imaginary numbers, and they didn't prove to be very practical in terms of technology. So they exist out there, but nobody really uses them for much. I, though, man, there's whole branches of math and physics and engineering built around it. So that's why we learn it in high school. And that's also why, the other reason we learn it in high school now is because, like, we're doing basic parabolas, very basic, and it comes up. Watch. So here's some examples of, not parabolas, but just things we want to simplify with I. Before, if I gave you this in the last couple assignments, you would have gone like, What? You could put it in your calculator. Your calculator would look at you and go, what? Error. But now we have a way to do this. 121, you guys know what square root?
11.
Is it 11? So the square root of negative 121, you should think about, you don't have to write it like this, I'm going to though. It's like negative 1 times 121. Can't you do this with square roots? Yes, you can. We're going to study square roots more specifically soon. You can do that with square roots. So this is, we just learned, I. This is, you guys just told me, 11. So really this is just 55i. Alright? Don't make these hard, because they're not. You just remember square root of negative 1 is now called I. Calculator can't even touch these. But the mind can. 96, that's not a perfect square root, right? We know this one's going to be I though because of this minus or this minus. It's the inside one that causes problems, right? So we know it's going to be like negative I something. That becomes the square root of negative 1. And then we got to break down 96. 96 is not perfect, but you can take stuff out of it. So you might be tempted to take 4 out of it. 4 comes out of it. That'd be nice. You always, when you do these, though, want to try to start with the largest thing you can, the largest square number that'll come out. You can use your calculator. Why don't you guys just fool around with your calculator, see which number will go in. 25 doesn't, obviously, right? 36 might. Tell me, what's the biggest square number that'll go into that? 64? Nah, not quite, right? Too big. 49? Nah, it'd be like 98. Kenan? 16? You guys see 16 going in? 48's not a square number, though. We're trying to pull squares out of this. 16 goes in? I think that's the biggest one, so I think you're right. So we can write this as negative I 16 times 6, right? That's what your calculator tells you. You can use your calculator to experiment with these. So this is negative 4I root 6. That's as simple as it gets. So imaginary numbers can have an irrational component. This one does. Okay? We all clear on that one? Okay, I'm going to move this one up here. Help me solve this one using yesterday's techniques. If you add it and set it to 0 and try to factor, you get this. We have a formula for factoring difference of squares. Sum of squares doesn't work though. Think about why. What's this look like as a transformation? There's the basic U-shaped parabola. What's that do to it? Goes way up, right? Like this is not to scale, but if this is 150, this guy looks like that. Does it have any zeros? Clearly no, it does not cross. Does that mean this has no complex solutions? You can't factor it. It doesn't have any real solutions, but it has complex solutions. How do you solve for x again? What's another way we learned? Square root. What's the square root of 144? What's the square root of negative? And I've made one big boo-boo. I used a square root, right? Gotta put my plus or minus. That should make sense to you because most parabolas have 2 roots. Not all, but most. In fact, all parabolas have 2 complex roots. So, there's the 2 complex roots. Can't see them on your graph. They're out there. Okay? Let's look at this one. What do you guys think if we're going to try to solve it? Should we just try like that one? Yeah, so first, solving for x. Oh, I want to divide by 5 now, right? 18? Am I right? Don't trust my math.
Yeah.
Okay. Square root, plus or minus side effect. Square root of negative is I. Square root of 18 is not nice, but it breaks down to 9 times 2. Oh, that's too tight. Clean that up. 3 root 2i. Oh, I forgot my side effect. Shoot. 2 roots. 2 solutions. 2 complex solutions. Do they show up on the graph? No, this guy, if you graphed it, would be up 90 and steep. It's not going to cross the axis. The real axis, anyway. So, don't be like me. Well, you can be like me if you want, but like, remember, I was, for all my first couple years of high school, even into college, I was still like, those imaginary numbers, what? What? Like, who cares? They don't even show up on the graph. People care. They matter. Let's do 2 more. So let's do some things where we find zeros. Two functions. I very carefully avoided giving you any problems like this before. The textbook / me avoided giving you these because we would have run into problems had we tried these before. Do they look like parabolas that are so different? No, they just look like parabolas, right? You could try to factor them. I mean, you come over here and say like, okay, like 13 times 2? Nah. 26 and 1? Anything else? Maybe you could try with like some fractions or something. You can try. You won't be successful. So this guy, it wouldn't have worked. Couldn't factor it. And if we'd have completed the square on it, this is what would have happened. Because that's what we're going to do. Magic time. What's the magic? 25. Half of 10 squared is 5 squared is 25. I got to compensate. How am I going to do that? I could either subtract 25 here, that's one option. We got an equation though, right? So I could also add 25 over here. You do what you like. Either thing will work. The reason we did that is because this is now perfect. X plus 5 quantity squared. And now we can solve for x. See, and right here we would have run into our problem if I gave you this one yesterday. Because you square root both sides here, and that you could not do, but now we know that is I. So this is plus or minus I. You guys tell me what's my last step to get x all by its lonesome? Subtract 5, right? So I'm going to have x equals negative 5 plus or minus I. A plus, there's no b, it's just 1 I. Okay. Let's see, that might happen on this parabola too, I'm thinking. So, magic time. I went for green over there. I'm going to go for green here. Can't just put random green things in an algebra problem. Unless I balance it by putting something there or here. I'm going to do it the other way this time, just to show you. If you add 4, you can subtract 4 to compensate. This compacts to x plus 2 quantity squared. Leftovers is 8. Subtract 8. Square root. It's imaginary again. Does 8 simplify the square root of 8? This is one I would memorize, by the way. Yeah, this is one to memorize. Square root of 8 is just so common. 4 and 2 go in, right? So that's 2 square roots of 2. One I would memorize. 2 square roots of 2 I. Move the 2, and you're done. Those are the answers. Your calculator cannot do them for you. There are machines that can do this, but they're way, way, way beyond our ability to use. So, well, we could use them. I could show you. Not worth it at this point. I'll see you next time.